accelerates. The tension on the cable pull the glider forward like this. There's another resistive force, Fr, which is 160 Newton backward, opposing the motion. Okay. The force that they ask is the tension. We have the net force, the resultant force is the sum of all the forces acting on the glider. The weight and the reaction force of the ground cancel each other out. So the the total force, the resultant force is the tension of the cable, subtract the resistive force 160 Newton. Okay.
Yeah.
The tension subtract the 160 Newton resistive force, and this net force is calculated by Newton's second law, ma, mass time acceleration, very familiar formula. Okay, here. So multiplying the mass 490 kilogram with the acceleration, what is the acceleration? We have to calculate that 27 minus 0 divided by 11. Okay, because we didn't do that, the calculation of acceleration in the question A, so we have to do it here. If in the question A you use this method, calculating acceleration, and using this formula, you don't need to repeat the calculation of acceleration, just get the value from question A. Okay.
Yeah.
This is the net force, and then the tension will be equal to that net force added with 160. Calculate this thing first. 27 divided by 11. 27 divide 11, and then multiply with the mass. The force here, round to 3 significant figures, is 1,210. 1,210 if we round it up. And then the tension is that thing, 1,210 plus 160 for the tension, plus 160, 1,370 if we round to 2 significant figures. The speed is 3 significant figure, the time 3 significant figure, the mass 3 sig also, huh? So we can use 3 sig fig, which is 67, okay, Newton. Or you can round to, I've checked the maximum, you can round to 1,370. Well, 70 here. 70 Newton, 3 sig fig, huh?
Yeah.
That's the tension. Did you do it correctly?
Yeah.
Okay.
Yeah. For this one, yeah.
The next one, capable electric motor. The motor has an overall efficiency of 23%. Determine the average power input to the motor. Power average. We have the definition of efficiency, which is 23% is the useful power. The useful power over the input power, the total power. The total power here is provided by the motor. The useful power is the energy to accelerate the glider. Okay, and that
Yeah.
useful power is calculated by the work of the motor, the tension, the work of the tension over the time. The time is 11 seconds, and the P total is the thing that we need to calculate. Okay, and therefore P total there at the bottom is the work over the time, and then divided by the efficiency for 23. Okay, the work is the force multiplied with the distance, force multiplied with the distance, and then divide the time and 0.23. Okay, the force is 1,370 Newton. The distance moved by the glider is 149 from question A. Okay, and then the time is 11 seconds, and the efficiency here, and the result will be about 81 kilowatt, 1,000 watt, 81,000 watt, rounded to 2 significant figure. Okay, check the calculation here. The work, the force is 1,370 multiplied with the distance 149 meter. Okay, and divide the time 11 seconds, and also divide the efficiency 23%. Okay, rounded to 2 significant figure, 81,000 watts, 81 kilowatts. Okay,
Yeah.
1 mark here for the formula, the second mark here, and third mark for the final result. Question D. After
I got
takeoff,
wrong
release.
for the C. I was wrong with this one. Yeah, I got it.
Power input to the motor, the total power. Over efficiency. This is the album useful output. Okay. Question D. After takeoff, the cable release and the unpowered glider moves horizontally at constant speed. The keyword is constant speed here. It means the acceleration is 0, and therefore the resultant force on this glider is also 0. Okay. The wings will provide lift force upward in this direction. The diagram shows the lift force acting on it. Complete this diagram. Draw the forces acting on the glider completely for the dotted line, so horizontal vertical direction. Okay. You just need to draw 2 forces, which is the weight vertically downward. This weight must be equal to the upward component of the lift force. Okay. But do not draw that component. Just use the ruler to measure this length and ensure that it equal to the length of this weight. Okay.
Yeah.
And the second force is the resistive force, Fr, of the air, and this resistive force is equal to this forward component of the lift force. Okay, so that the sum is 0. The net force, the sum of these 3 forces is 0. Okay, when you add the weight here with the resistive force Fr, you have the sum of those 2 forces in this direction, the diagonal of this rectangle. Okay, this is the sum of W plus Fr, and this sum is equal to the lift force upward. So the resultant force, the sum of the 3 forces, is 0. Okay.
Yeah.
Okay, this is the diagram. Question 2. Outline condition necessary for simple harmonic motion to occur. The net force must be proportional to the displacement. The resultant force acting on this object, resultant force acting on this object is proportional to the displacement of the object. Okay, and pointing toward the equilibrium position. Equilibrium position direction is 1 mark, and proportional displacement is another mark. On the object is 2 mark. First mark here, second mark here is proportional to the displacement of the object. Displacement, and secondly, it points always toward the center, the equilibrium position of the object. Okay, always point towards the equilibrium position. Okay. Question B. A buoy floating in a vertical tube generates energy from the movement of water waves on the surface of the sea. When the buoy moves up, a cable turns a generator on the seabed, producing power. When the buoy moves down, the cable is wound in by a mechanism in the generator and no power is produced. The motion of the buoy can be assumed to be simple harmonic. Wave amplitude 4.3 meter per meter and a wavelength of 35 meter moves with speed of 3.4 meter per second. Calculate the maximum vertical speed of the buoy. Okay, that vertical speed will be equal to how many times? When it oscillates 1 complete cycle from the bottom to the top, completing 1 cycle, meaning bottom to top and then bottom again, the time is one period, and that period is equal to the period, the time interval between the two peaks of the wave, of the two successive waves. Okay, that period, the speed is the distance. We need a distance is the 2 times the distance between the top and the bottom. Amplitude, okay, the amplitude, the wave amplitude. This is the equilibrium position of the wave, the middle point. The amplitude is from the midpoint to the top. Okay, amplitude. So when this buoy is moved from the bottom to the top, it's moved 4 times the amplitude. 2 times when going up from top to bottom to top, okay, and 2 more amplitude from the top to the bottom, meaning the distance is 4 amplitude. I'm calculating the speed, 4 amplitude, and divide the period of that object. The period of this buoy moving up and down is also equal to the period of the time interval between the two crests of the wave passing through that point of the buoy. Okay, and that period is we have the wavelength lambda of the wave is 35 meter, is equal to the speed of the wave, which is different from the speed of the buoy moving up and down. Okay, the speed of the wave, another thing, which is 3.4 here. 3.4 divide the period, and therefore the period here can be calculated by 3.4 meter speed divided by 35 wavelength. Okay.
Yeah.
The wavelength equal to this thing. So the period is 3.4 divided by 35, and the 4 times the amplitude is 4.3 meter. Okay, so this is the solution. 3 mark. Okay, calculate that. 4 times 4.3, and then divide 3.4 for the speed, divide wavelength 35. Okay, 177. If we round to 2 significant figure, it will be 180 meter per second. Very fast, huh? It doesn't make sense. Something wrong.
Yeah.
Because it's fast, too fast. Let me check the math scheme. I haven't solved this problem for a long time. Okay, the period is the inverse of my solution. There's something wrong. Oh, okay. So sorry. This is the wrong formula for the wavelength. Wavelength is the speed over frequency, not over a period. It is the speed multiplied with the period. Okay, I remember the wrong formula. Divide frequency, not divide period. Multiply the period actually. Okay, and
Yeah.
therefore the period is the wavelength divided by the speed, which means 35 divided 3.4. 35 divided 3.4. Okay.
Yeah.
4 times 4.3, and then divide 35 divide 3.4. 1.67. It makes sense now. 1.67. We can round to 1.7. Checking answer. Different. 2 pi x0. The speed, the time, the buoy. It's the time. This 2 pi x0 is omega, meaning angular frequency. The speed, wave amplitude, wavelength. Okay. Amplitude. Okay, it's not for A. Okay, the oscillation of this buoy is the same as the wave. It is same as any single molecule in the wave. It is vibrating with the wave, with the same frequency, with the same speed. And the speed they ask here, the vertical speed of the buoy, is the speed of the oscillation of one single molecule oscillating up and down. Okay, let me show you the nature of the wave again. Water wave particle. Actually, they on an ocean, for example, water wave particle oscillation. Those particles do not oscillate vertically up and down, but oscillate in a observe a single particle here on the surface. Okay, it is oscillating in a circle, moving like in a circle, not perfectly up and down. Okay, but for this problem, we assume that anyway, just the boy is placed particularly like that in a tube. Yeah, in a tube, and therefore it can only oscillate up and down. And okay, there's a formula in the topic 9 here. Topic 9 about symbol harmonic oscillation. Here, the period. Omega in this formula is called angular frequency. Okay, and we need to find the speed v. Here, using this formula, you can use the first one here or the second one here, but normally 99% they use the second one. The question is maximum speed. The maximum speed is when the value of the psi function is 1. Because the psi function vary from -1 minimum value to the +1 maximum value. Okay, a psi function cannot have a value greater than 1, and therefore this speed is maximum when sine of omega t is 1. Okay, meaning the maximum speed is determined by omega times x0. Ignore the negative sign. Omega times x0. Okay, just write that formula. V is omega times x0. X0 is the amplitude, 4.3 meter here. Okay, omega is determined by the first formula here in topic 9.1, 2 pi over t. Okay, 2 pi over t. And t, again, you write another formula for t. It is the wavelength over the speed. Wavelength over the speed. Okay, so and times x0 to get the v. Final formula, 2 pi x0 times v over lambda. Okay, or you can calculate the period first and then plug in here. Okay.
Yeah.
2 pi x0 is 4.3 meter. The speed is wait. The speed, move with the speed. This is the speed of the wave. Speed of the wave is different from the speed of the particle oscillating up and down. Speed of the wave. The distance that the wave travel in 1 second. Okay. The distance, the wave travel from the left to the right. For example, we see wave particle. We see here 1 point, the red point, indicating the peak of the wave moving from left to right. So that is the speed of the wave. Okay, the speed of the wave moving from left to right with peak moving left to right is different from the speed of oscillation of the molecule up and down. Okay, the speed in this is the speed of wave 3.4, and then divide the wavelength 35, and we get this final answer. 2 pi times 4.3 times 3.4, and then divide 35. Okay, 2.6. Okay, take into significant 2.6 here. Meter per second. With the speed of the boil and also of the water molecule, maximum speed of the boil. Okay, UOY. Okay.
Yeah. Okay.
Most students will, make the mistake and cannot answer this one correctly. This is a hard one.
Yeah.
Scale the graph to show the value with time to generate the output power level over time with a suitable scale. The output power cannot be negative, huh? and the power is produced only when the buoy is moved up. When the buoy is moved up, the cable turns the generator on, simply producing power. And when the buoy goes down, it does not produce the power, and therefore the power is the peak like this, the pulse, the sinusoidal pulse like this, separated by like half the wave, okay, half the period.
Yeah. Mm-hmm.
A sinusoidal wave with half the period. Try to make it as symmetry and as smooth as possible, huh? Not as okay, like this. This position is half the period. This is one period. The period was found to be 35 over 3.4, which is 35 over 3.4, 10.3, huh? 10.3 second. So it's a half of 10.3 here, 10.3 second here, okay?
Yeah.
Half of 10.3 is 5.15, okay, and so on.
Yeah.
Yeah, and they rounded to 10. How many? Okay, it doesn't matter if you draw like 3 pigs or 4 pigs, huh? Like in this case, I saw only 2 pigs.
Yeah.
The thing that is matter is the time here and the shape of the output power.
Mm-hmm. Yeah.
The alternating current that we use every day, lighting the light bulb, running the fan in our room, is a sinusoidal wave like this. Question 3: the water can be used in other ways to generate energy. Outline with reference to the energy changes, the operation of the pump storage hydroelectric system. Energy change, the operation of the pump storage hydroelectric system. Energy change, okay. The gravitational potential energy of the water stored in the dam in the storage, okay.
Yeah.
Gravitational potential energy of the water stored in a dam convert into the kinetic energy of the flow water
Mm-hmm.
of the water flow, and then to the rotational kinetic energy of the turbine, of the generator, okay, and finally to the electric energy produced by the generator.
Mm-hmm.
You can skip this part, okay,
Yeah. Okay.
or you skip the second one here, to the rotational, to the flow, and then make the turbine rotate and convert into the electricity energy,
Mm-hmm.
electrical energy. Water in a particular pump storage hydroelectric system for a vertical distance of 270 meters to the turbines. Calculate the speed at which water arrives at the turbine. Assume that there is no energy loss in the system. That distance, speed at which water arrives at the turbine. No energy loss in the system. Okay, we can use the conservation of energy here. Consider an amount of water waiting with a mass m. At this height, 270 meter, this height is called h. It has this potential energy, mgh. Okay, that
Yeah.
kinetic potential energy will convert into the kinetic energy of the water flow at the bottom of the dam. The dam is huge, and there is a tunnel at the bottom of the dam like that, huh? So the water flow through and rotate the wind turbine at the turbine of the generator. Hydroelectric generator power plant. Yeah. they build a dam up here, and then there's a channel for the water to flow through. Okay, rotating the turbine and produce electric energy. Not necessarily at the bottom of the dam. Okay, and they have to store some water in that dam anyway. The channel, the tunnel here is not at the bottom, but for this problem, we have to assume that this height, 270 meter, is from the surface of the water to the tunnel of the flow. Okay.
Yeah.
A vertical distance. Okay, the falling distance, that definitely 270 here. The mass doesn't matter because they cancel each other out. I can consider 1 kilogram mass or 1 ton because the same, amount on both sides of the equation. G is 9.1. You can take to 9.181, 1/2 of the speed v square, and then we can calculate v, huh?
Yeah.
2 times of this thing is square root of 2 times 9.81, and then times the distance. 73. We round to 2 significant figure. 73 meter per second. Checking answer. Potential energy, convert to moving water, convert to the turbine, and produce electricity. Specific energy available, GH. Okay, using this one, huh? Yeah, 73.
Yeah. Okay.
Hydroelectric system has 4 250 megawatt generators. Determine the maximum time for which the hydroelectric system can maintain full output from the stored energy with a mass of 1.5 10 to 10 kilogram of water passes through the turbines. Maximum time for this is the power. The power is the energy divided by the time, and they ask for the time. We need to find the time. Full power, the mass through the turbine. Okay, this energy must be equal to the initial original source of energy, which is gravitational potential energy, mgh. And we can use the distance 270, huh? Or use that speed. Yeah, I think we can use the speed given there. 1/2 of the mass m. The mass is, okay, just write the formula first and then value later. mv square or mgh, and then divide the time. 4, this is 4, so the power, the value of the power is 4 times of 250 megawatts, so we need to convert that into watt and multiply with 10 to the power 6. Okay, and then that the mass is given there, 1.5 times 10 to 10 kilogram, 15 tons of million tons, huh? Trillion tons of water. And then time the speed, 73. Did we round it? Okay, I think if we can round it hit there, huh? 73, or you can take the high, use this formula, huh? Okay, and then divide the time. So we can find the time from this one, from this formula. Okay, the time, meaning how long for the water to pass through these 4 generators or 4 turbines to produce with amounts of energy in 1 second, because this is the power, meaning the energy produced in 1 second. Taking this left side, right side, divide the left side, 1/2, 0.5. If I take the accurate value here, huh? The mass is 1.5 times 10 to power 10. And then I take the accurate value here for the speed, huh? And then square it, and then divide the thing on the right, which the left, which is 4 times the power, 250 megawatt times 10 to the power 6 to convert to the watt, huh? So this is the answer. Almost 40,000 seconds.
Yeah.
40,000 seconds there. Beautiful. Okay. 40,000, 4.0 times 10 to 4 second. We can convert into hour to make it more readable, understandable, huh? Take this value and divide 3,600 to get the hour, huh? 11 hour.
Thank you.
Okay. Not all the stored energy can be retrieved because the energy losses in the system explain two such losses. The losses where the heat produced in the turbine, in the generator, there's always the heat. There's no way to, make the heat become zero, huh? Absolutely no way. That is a principle of the universe. That is one reason of the loss. What's the other loss? The flow of the water is not steady. It can cause some, what's that called? Stir or something, the turbulence in the flow of the water. Okay, but I don't think that will be in the mass scheme. The turbulence. Okay. Sound energy. Okay, sound energy, thermal energy, water require kinetic energy to leave the system, so not all can be transferred. Okay, and anyway, the kinetic energy of the water after passing through the turbine is not zero. The water keeps flowing out of the turbine, so that not 100% of the kinetic energy of the flow water converting to electricity. Okay, so the two reason of the losses. The thermal energy or the heat produced in the turbine and the generator, huh?
Yeah.
A lot of heat actually. We need a very good cooling system. And secondly, the sound energy to the surrounding, and also another reason, not all the kinetic energy of the flow converting to electricity, but some remaining kinetic energy of the water flowing out the turbine of the generator. Okay, not all kinetic energy of the water flow converts into electrical energy, because the flow still has kinetic energy when flowing out, huh? to flow out. Question 3. Electrical circuit shown in use to investigate the temperature change and wire is wrapped around a mercury glass thermometer. A power supply EMF 24 volt and negative internal resistance connected to the capacitor and the core resistance wire using arrangement of two switches, which S1 close and a few seconds later open. S1 is closed, so we can charge the capacitor here, allowing the electron to run from the negative terminal here, the battery, to the plate here at the bottom, okay, and inducing and pushing the electron on the top plate to the other end of the battery, charging the battery, and then open it so that the charge stay there, stored in a capacitor, okay. Then close the switch S2 so that the electron leaves the capacitor discharges, forming a current. In a very short time, the electron go from the bottom plate to the top plate. Okay. The capacitance of the capacitor 22 microfarad. Calculate energy stored in the capacitor when it fully charged. Just find a formula in the booklet for the energy of capacitor. As I remember, 1/2 CV squared. C is the capacitance and V is the voltage between the two plates of capacitor. Energy. Okay, here 1/2 CV squared. Okay. Yeah. 1 mark 1/2 CV squared. Like kinetic energy 1/2 MV squared, huh? C is 22 microfarad multiplied with 10 to negative 6. And then the voltage is 24 equal to the maximum EMF, assuming that the time is long enough for fully charge the capacitor to the maximum EMF 24. Okay, 24 square here, and we get the final result. 1/2 of 22 convert to farad, and 24 square. 0.06, or I can write 6.3 times 10 to negative 4, huh? Negative 3, negative 4, negative 4. 6.3 times 10 to negative 4 joule. Okay.
Yeah.
Wait, 6.4 joule, no conversion. Volt microfarad, negative 6. Something wrong here, huh? Micro. Oh, sorry. That's not micro. That's millifarad. Milli, so negative 3 only, not negative 6. And therefore reducing this one to okay, 6.3 joule. Okay.
Yeah.
6.3 joule. Millifarad, not micro. Question B, the resistance of the Y is 8 ohms. Determine the time taken the capacitor to discharge through the resistant wire, assuming that the capacitor completely discharged when the potential even across it has fallen to 0.24 volt, which is the final voltage on the capacitor. So you can use the formula for the discharging process, which is this one, V. Okay. V equal, let's calculate the time constant first. That thing tau is called the time constant. It is the product, meaning the resistance multiplied with the capacitance. Okay.
Yeah.
Resistance is 8, capacitance is 22 millifarad. There. Calculate this thing also. 8 times 22 times 10 to negative 3. 0.6176. 0.176, and it unit is second. The formula V is V0 times e to the power minus the time that we need to calculate, the time t that we need to find, divide that time constant tau, which is RC. Okay, RC. There, use that formula. V here is the final voltage, 0.24. Okay, the initial thing here is 24. E to the power of t over that thing, 0.176. Put this into the calculator, you can find the t, the time t. Can you do that?
Yeah.
Okay, so please use the calculator, calculate the time. Tell me. If you don't know why, I can help you with the calculator like Texas 84 something, Casio.
It is 0.58.
0.58 second, comparing with the mark scheme. Answer is 0.81. 8 times 0.02. 1 over 100. 24. Simple lab. Solving equation. Of course, I can use a calculator like TI and Texas, but using this one is faster. 0.24 equal 24 exponent exponential our minus. Did I forgot the minus? No. Yeah, minus. Did you forgot the minus?
No, I didn't.
Minus of x divided by 0. Check this thing also. 8 times 22, huh? 22 or 2.2? 22. 0.176. 176. So, okay. And x, wait, the value of x here is not so for. Do they understand this thing? Is it different, huh? Okay, anyway, this thing will be a positive value, which is ln of 0.01, because ln of is number less than 1 is a negative value, and then multiply with negative 1.76. Okay, here you see, that's the problem with your calculator. One step that you did wrong somewhere, do it again. Let me share my screen using switch screen window. You with calculator, do you have the same thing here?
Yeah.
Texas TI-84. Do you use it or another one?
No, another one. The more the like graphical.
Casio.
No, TI Inspire CX.
Okay, I know that, but I don't have it installed on my computer. I used to use that one, but it's very similar to this one actually. Anyway, okay, we are solving that formula, huh? That equation. Okay, math solving equation. Solver here, huh? And then I need to enter the function, the equation. Clear. The equation is okay. I need to subtract 0.24 later. 24 here, multiply with x to the e to the power of negative x, which is the time, divided by 0.176. And then I need to subtract the left side, huh? Subtract 0.24. And then I have to guess a solution, guessing one, and then alpha and solve. Yeah, 0.81. See?
Oh, I got 0.81. I just like plug in the wrong like the place.
Okay, 0.81.
Yep.
Time constant. The meaning of time constant in the capacitor. The time constant is the time so that the charge on the capacitor, the energy on it, now the voltage on it, dropped by 63%. Capacitor. Okay, this is the graph of the voltage. Okay, after one time constant, the time constant is the resistance R multiplied with the capacitance C. The voltage, sorry, this is the current. The current decreases during the discharging process, okay, to 47%, which means the drop is 63% in one time constant, okay. That is the meaning of the time constant. Okay, next one. The mass of the resistant Y is 0.61 grams, and it observed temperature rise 28 Kelvin. Estimated the heat capacity of the wire. Include profit unit. Heat capacity, the formula is E equal mc delta T. Huh? We have to determine C. C is E divided by m delta T. Okay, energy, resistance Y. This is the resistance. Energy we have, okay. The voltage decreases. The energy Okay. We need to do one more step to calculate the energy. Energy is the initial energy of the capacitor subtract the final energy of that capacitor. One half CV initial square, or we can write 1/2 of capacitance 22 times 10 to the negative 3 capacitance. Energy of capacitor is 1/2 CV square. Okay, I'm gonna subtract the initial energy. Initial voltage here is 24 volt. Subtract the final energy of the capacitor, CV final square, and V final is 0.24 volt. Okay.
Yeah.
To get the energy that the capacitor releases in that time, 0.81 second. Okay.
Yeah.
Multiply with 24, and then I can combine. I can make 1/2 C the common factor. Okay. 24 square subtract 0.24 square. Okay, you got it right. Basic math algebra.
Yeah.
This is the energy that the capacitor releases in 1 second. In that time, for 1 second, huh? 1/2. Multiply with 22 times 10 to negative 3, converted to farad, times 24 square minus 0.24 square, and have this result 6.3 joule. 6.3 joule. Okay. Yeah. Which is very close to the initial energy here, because the value 0.64 is too low. It's almost zero. Okay, compared to 24, it's like 100th, 100% of the initial energy. So the specific heat capacity here, if this energy 6.3 divided mass here, which is very low, for 61 gram, we need to convert that into kilogram also, huh?
Yeah.
And temperature 28, and finally we get the result. Can you do this one? I mean, in the mock test.
No, I got wrong.
Okay, divided by the mass 6.1, converting to kilogram 10 to the power 83, and then times the 28, huh? Temperature change 36 rounded to 37. 37 joule per kilogram per Kelvin with the specific heat capacity. One wrong number. 370. Something wrong with this calculation. Times 10 to negative 3. 6.1. Oh, 0.61. 0.61, but I put here 6.1, huh? Okay. So that's definitely 370. Okay.
Yep.
0.61. So the hardest part is understanding how to calculate the energy, right?
Yeah. Yep. Got it.
Only question 3. 1 hour already. So just one energy loss. Anyway, to get a 6 according to the Great Barrier last year, you only need about 53%.
Yeah.
Of the test.
Oh, my friend said someone from the other class got 1 from paper 1.
So just 1.
Yeah, like 1 out of 7.
So just 1 energy loss in the experiment, and the effect if we have on the value on the heat capacity of the Y. 1 other energy loss in experiment, and the effect it will have on the value of the heat capacity of the Y. Energy loss is mainly because of one reason is the heat here that we calculated in C1. Another energy loss, electromagnetic energy, electromagnetic wave emitted to the surrounding. Energy loss in the Y. Yeah, and the energy transfer from the thermometer to the surrounding, thermometer to the surrounding. Okay. Some thermal energy will be transferred to the surrounding along connecting wire to the thermometer. Okay. So, the energy can be lost. Transfer and effect we have on what other energy loss? Okay. Heat transfer to the surrounding from the liquid in the thermometer. Okay. Transferred to the surrounding from the thermometer, and the effect on the space on this calculation of the specific heat capacity, because here we use fit energy 6.3 joule with the assumption that there is no energy loss 100%, but in reality the real value is lower than this one, lower than 6.3, and therefore the heat capacity must be lower. Okay.
Yeah.
The specific heat capacity C must be lower than the calculation in part C, because the actual energy transferred to it is less than 6.3. The actual energy transferred to the thermometer is lower than 6.30. Yeah. Next one, question 4. Investigate how light can be measured using the speed of the toy train.
This was the question that I got wrong, like most of it.
Okay.
I
Light
know.
from a laser incident on the double slit. The light from the slit is detected by a light sensor attached to the train. The graph shows a variation with time. The output voltage from the light sensor as the train moves parallel to the slits. The output voltage is proportional to the intensity of light incident on the sensor. Explain with reference to the light passing through the slit why a series of voltage peaks occur. Okay, this is the transfer from the intensity of light reaching the sensor to a voltage, a signal on the monitor of a computer. Okay, transferring from energy, light energy to voltage signal, and this output voltage is proportional, mentioned here in the statement, proportional to the intensity of light. And this is a pattern, the display of the intensity of light formed by interference and diffraction at the same time. So the explanation here we can write why a series voltage peaks occur. Okay, the pattern of the voltage is similar to the actual distribution of the light intensity, which is an interference and diffraction happening at the same time. Okay, occurring at the same time. Okay, increasing the size. When the waves from the two slits are in phase, they interfere constructively, forming maxima when or at some location, at some locations, and at other locations, the waves are out of phase, cancelling out each other, forming minima. The decrease of the intensity is because of the diffraction when the phase difference of the waves are not 180 degree. The phase difference when the phase difference of the waves varies from place to place. Okay.
Yeah.
Answer C. Light superimpose, interfere, particles, intensity, maximum, minima, constructive, destructive. What the peak response to interference maxima? Okay, basically the similar idea. If you see a paragraph, try outline the main idea. If you're running out of time, not writing the whole paragraph, just outline main idea, getting at least 2 marks, mentioning interference and constructive and destructive interference, maxima and minima. Okay.
I don't think like I'm really like chased by the time, but I think the accuracy of my answer is like the problem when I solve the question. Because when I'm solving it, like I think that I'm right, but if I look at the mark scheme, like there are lots of questions that I got.
So that is the error about the method, not about the math calculation, right?
Yeah, just the method of calculating. Yeah.
We have no clue how to, or the way, like an entirely different approach. The way, like we don't know how to get the energy here, or to calculate the power in this problem.
Yeah, sometimes like I use the different equations or like that.
Okay, the only way practice. We have one month left. Like try practicing 4 paper a week, 2 paper 1, 2 paper 2, and 1 paper 3 also. The slit separated by 1 millimeter, and the laser light wire has a wavelength of 6.3 × 10⁻⁷. The slit of 5 meters from the train track. Calculate the separation between the 2 adjacent positions of the train when the output voltage at the maximum. Okay, there's a formula, and I remember it's not in this booklet here. I'm thinking about this one. There's a formula not given here. D sine theta, another angle. From this formula to form the equation that I think is the solution of this question, that formula is the separation equal to the lambda wavelength lambda to times the distance from the slit to the string big D divided by the separation between the 2 slits. This formula not given. Okay, and to prove this one, it takes a long time, a whole page. So hopefully that you can memorize this thing. This one, calculate that slit separation, separation between 2 adjacent positions of the train. Okay, that slit separation is the wavelength multiplied with distance between the slit and the train divided distance between the 2 slits. The slit separation is 1.5 millimeter here. This is small d. Okay.
Yeah.
We need to convert them into the same unit, such as if I put here millimeter, just make meter first, 1.5 millimeter times 10⁻³ convert into meter. Everything, every quantities in this formula must be in the same unit, meter. The wavelength 6.3 times 10⁻⁷, and the distance big D is 5 meters here. This is big D, this is small d. Okay, 5 meter here. So we see only one map, but it requires memory by this formula, which is not even.
Yeah.
And most students do not remember this thing actually.
Yeah.
Vietnamese student, I used to thought I, made them memorize this thing by heart by doing a lot of exercises. With length 6.3 times 10 to negative 6. Oops. Negative 6. Negative 7. Times the big D 5 meter and divide the small d 1.5 times 10 to negative 3. 0.01021. 0.0021 meter. You can convert to millimeter, huh? 1, 2, 3, 2.1 millimeter.
Yeah.
Here, millimeter.
Yep.
B2, estimate the speed of the train. Read the statements. To find the speed, we need the distance here. The time, we need the time that the train moves this distance. Where's that? The time. Okay, the time is determined on this graph. The time between the two peak here, from this peak to this peak, is almost 25. Is that like 20 or 25? You can use a ruler to determine this.
Yeah.
The real paper 25, I assume,
Yeah.
So the time is 25 millisecond compared with the mass scheme. Yeah, 25 millisecond. So that speed is the distance, the speed of the train, distance the train move, which is 0.0021 meter, or square centimeter rotation, 2.1 times 10 to the negative 3. Divide that time, 25 millisecond, convert to second. Okay, 25. 2.1 divide 25. 0.084. 84 meter, right scientific notation, 8.4 times 10 to negative 2, Okay.
Yeah. Yeah.
Yeah. The distance in time of the two peaks is the time that the train move between those maxima. Okay. Question C. As the train continues to move, the first diffraction minimum is observed when the light sensor at a distance 0.13 meter from the center of the fringe pattern. The minimum they are talking about here, 0.13 meter from the center, is this place. This is the first diffraction minimum, and also the the darkest minimum. The first diffraction, is that called diffraction? Diffraction rating, yeah. Diffraction minimum. Normally, when we do an experiment of double slit, interference, and diffraction envelope, the diffraction also occur at the same time with the interference. Without GeoGebra, yeah, I don't remember if I showed you this thing before, but I showed many other students.
Yeah.
If we reduce, we say the diffraction envelope, okay, interference. If we can reduce the width of each slit to be very small, this is like millimeter, but if we reduce that, the intensity of the outer maxima will be higher and higher, will be almost equal to the intensity of the central maximum. Okay,
Yeah.
meaning when the width of the slit is extremely small, comparable to the wavelength, it is only interference, because the slit is too narrow, so that it is like only two waves, one way passing through one slit and two way passing through the two slit. Okay, but if we increase the width, now from one slit, one way can separate into many ways. And among those many ways can be 100 ways or 1,000 ways. Some way can be different in phase by 30 degrees, some way different by 60 degrees, some ways are different from each other by 45, 70, 90 degrees, etc. And therefore it will reduce the intensity of the outer maxima. Okay, outer maxima. Increasing the slit width will reduce the maxima. And the envelope, the diffraction here, we see the first minimum of the diffraction envelope. When you do the experiment with only single slit diffraction, have a pattern like this one, which is very similar to diffraction to the double slit, because in the double slit, the interference of each single slit also occur. Okay, this is single slit pattern, with the double slit pattern. They look very similar. But for double slit, actually there are many secondary maxima, and here's like one single continuous band. Okay.
Yeah.
This is by changing the slit width. Very narrow, you have more secondary, maxima, and increasing the number of the slit. Interference slits number increase here. For single slit, we have this pattern: 2 slit, 3 slit, and so on. Meaning increasing the slit will make more maxima. They are more distinct from each other, more, separated from each other, easier to observe their separation. Okay, and also will be the brighter. Okay.
Yeah.
So the distance from the center maximum here to this point is 0.13 meter, according to the next question. Here, okay, 0.13. And my advice, you only need to aim for 60%, 55% of all the questions, 80 or 95 mark. You aim for like 50 or 55, 60. Okay, so focus on your strength and skip some part which are your weaknesses.
But my biggest concern is paper 3.
Okay.
Because paper 3 is really hard for me.
Okay. We'll
So
practice paper 3 next time.
Yeah, so I have to like do my best on paper 1 and 2. So I have less pressure.
Okay, we practice another paper 3 next week.
Yeah.
Determine the width of one of the slit, and this first diffraction is the first maximum of interference here. Second maximum interference, meaning 2 small s separation. This is s. This is also another s that we found s by lambda big D over small d, which is 2.1 millimeter. Okay. Another s here, that is 3s, 4s, 5s, and 6s. Okay, 1, 2, 3, 4, 5, 6. Okay, so that is 6s. The distance 0.13 meter here is 6s way. S is 2.1. 6s is not this thing, huh? 6 times, wait, 2.1 is 12.6. You see, almost 1.13. Okay, 2 millimeter multiplied with 6, 2.1 millimeter. So basically 12.6, approximately 13 millimeter. 13 millimeter. That means 1.3 centimeter. 1.3 centimeter. 0.13 meter. Yeah. That's correct. 6s, huh? Yeah, that's 6s. And S is the separation between the two maxima that we found in the question D1, huh? D1, C1, something here. 2.1. Okay. B1. 6s. Determine the width of one slit. the width. Okay. That is the first diffraction minimum, and therefore we can use this formula for the single slit. This formula. Determine the width of one slit. That formula, lambda, the angle theta equal lambda over b. Theta equal lambda over b. B here, the width that we need to find. What is b? Okay. So we need to find the angle lambda there. The distance d from the slit to the train track, is big D was 5 meters. Okay. And this distance here, between those maxima is 0.13 meter. So the angle here can be found. Okay. Where theta, tan theta, you see, this is opposite and this is adjacent. Opposite is 1.313, 0.13, and adjacent is 5. Okay. Tan theta equal 0.13 over 5. And therefore you can determine the value of the angle theta. Okay. Will be very small. So theta equals something, and then from this thing you can determine b, which is lambda over b. Lambda is 6.3 times 10 to the negative 7 meter. Okay.
Yeah.
And divide that theta. You get a final result. Okay. Please do the calculation for me.
Yeah.
Calculate the angle theta, and that angle will be very small, and therefore the tan theta will be equal to theta measured in radian.
Yeah. But that's too small.
Yes, it is very small.
Is it 2.4 times 10 to the negative 5, the B, the final answer?
Sorry, can you say again? Check my answer here.
2.4.
Yeah, times 10 to the negative 5.
Times 10. Yeah.
2.4 times 10 to the negative 5 meter.
Yeah.
We can round to micrometer, 24 micrometer. Yeah, very small. Suggest the variation in the output voltage from the light sensor that will be observed as the train moves beyond the first diffraction minimum. Variation in the output voltage from the light sensor that will be observed as the train moves beyond the first diffraction minimum. There will be some other secondary maxima, but very low intensity here. The secondary maxima, very low compared to the central maxima here. Okay.
Yeah.
So it's about memory also. There will be, or there are some other maxima of the voltage display on the monitor, but with very low value or intensity, very low values, just like that. Voltage minimum spacing possibly the same. Okay. Rate of variation in change rate of variation change beyond the first reflection average voltage is smaller, correct, 1 mark, okay. Maxima separated by the same distance, okay, separated by the same time, by the same time interval on the graph, okay.
Yeah.
At the same time interval, separated at the same time interval. Yeah, the distance between these peaks here at the same time, such as 25, that is 25 millisecond. Question D. Wow, this is very difficult and long, huh? The paper before the upgrade of the IB in 2019 was very long like this, and it is being changed, and the recent change happening this year and apply from the next year will be even easier than this today. With no paper 3.
This paper was really. When I like first got the paper in the exam center, I was like blanked because it was too thick.
Now it's very simply replace the size sensor with the sound sensor. The train travel away from the loudspeaker, that emitting the sound wave of a constant amplitude and frequency towards a reflecting barrier. The graph showed version with the time of the output voltage of the sound sensor. Explain how this effect arises. This is a standing wave of the sound. This standing wave is the result of the interference of the incident sound produced from the loudspeaker and the reflected sound from the barrier. Okay, and the maximum and minimum 2 marks. The signal, the variation of the voltage indicates the standing sound wave produced by the superposition positions of the two coherent wave, coherent wave, meaning same frequency, same wavelength, same frequency, the two coherent waves. Firstly, that is the way the sound wave from the speaker and the reflected wave from the barrier. Okay, I think we just need answer like that. That 2 mark. If it is like 3 mark or 4 mark, we put another more detailed explanation about the out of phase waves canceling each other out, resulting minimum, and in phase waves enhancing each other, forming maximum. Okay. Reflection lead to a totally opposite direction. Mention transformation of standing wave. Maximum correspond to antinode maximum. Okay, one more sentence. Wow, too complicated. The maximum are at the peak of the signal, Okay, at the node, maximum at the antinode of the standing wave. Maxima, plural form, and the minima are at the nodes. The first anti-different alphabetical different method were Rutherford and Royd. They knew that radium decay by alpha emission to form the granode radon. Write the equation. Radius 88226, decay alpha, which is helium-24 nucleus, forming a new thing, radon 88 minus 2, and 226 minus 4 is 222 here. Done. Okay. Too easy mark. At the start of experiment, Rutherford and Royce put 6.2 times 10 to the negative 4 mole of pure radium in a small closed cylinder. The cylinder is fixed on the center of the larger closed cylinder B. The experiment lasts for 6 days. The decay constant radium is visiting. The user activity of radium is almost constant during the experiment. Activity is the product of the decay constant lambda. Yeah, this is decay constant lambda and the remaining nuclide. The remaining nuclei N is the initial nuclide, which is this number of mole N multiplied with the Avogadro number to get the initial nuclide. Okay. And multiply with e to the power of minus lambda times the time t. And we are proving that this activity over the time t, which is 6 days, is almost the same with the initial activity. Or as long as this lambda, you see this thing, you can say, I think, I'm not sure, I'll check maximum later, that because this decay constant is very small, and therefore the activity here will not change in a short time, but it only change countably when the time is very long. Okay.
Yep.
6 days. Oh, they're using that. Yeah, they're doing the same method with what I'm doing, proving that the activity is almost constant. Okay, plugging the value in here. The lambda is 1.4 times 10 to negative 11. N0 is the number of mole multiplied with Avogadro number. Number of mole is 6.2. 6.2 times 10 to negative 4. Avogadro number is 6.02 times 10 to negative times 10 to 22. Okay, you can check this value in the booklet. Then times e to the power of the time 6 days. This is in seconds, so 6 days there. I need to convert it to second also. 6 days, 24 hour, 3,600 second. Okay, and divide, not divide, multiply. Wow. Okay, this whole thing is the power has 6 days. 6 days, 24 hour, 3,600 second, and multiply with the lambda. Lambda is very small, 1.4 times 10 to negative 11. Okay, negative 11 there. And do this calculation, you see that it is approximately constant, the same with lambda 0. With A0, you need to calculate A0 also. Approximately the same with lambda N0. Lambda N0 is A0. Let me write here. A0 is lambda times N0. Okay. That's too long. Very small. So activity only change in a very long time. Activity only changed in very long time. Okay, so that's a lot of calculation. This is the method. So that is the amount alpha particle emitted by the radium in 6 days. That amount of alpha particle is calculated by the initial amount of the particle subtract the remaining particle. Okay, N0, and the remaining is N0 times e to the power of minus lambda times t, and therefore I can put the common factor here, 1 minus N0 times e to the power of lambda t. Okay, and N0 is the number of mole, 6.2 times 10 to the negative 4 multiplied with Avogadro number times 10 to 22, and then 1 minus, oh sorry, this is no 0, no N0. 1 minus e to the power of that lambda, 1.4 times 10 to negative 11, multiplied with 6 days, 24 hours, 3,600 seconds. Okay. Oh dear. And that will be about this value. Okay. Hello.
Oh, I was turning off the mic.
You got it, right? This N is the remaining nuclei.
Yep.
This is the initial. At the start experiment. Wow. Wow. It
is too long.
Paper before 2019. At the start experiment, all the air was removed from cylinder B. The alpha particle combined with electrons as they moved through the wall of the cylinder A to form helium gas in cylinder B. The wall of cylinder A is made from glass outline, while this glass has to be very thin. One mark, very thin, because the alpha particle has very low kinetic energy. So if the wall is very thick, it cannot get through the wall. Okay. The alpha particle has very low kinetic energy. The wall must be thin so that they can get through. Okay.
Yeah. Yep.
Experiment was carried out in a temperature of 18 degrees. The volume in cylinder B was small, and the number of cylinder A, the volume of cylinder A was negligible. Okay, A, the thing inside, very small compared to B. Calculate the pressure of the helium gas that was collected in the cylinder B over a 6 days period. Calculate pressure. Okay, we just need to use the formula of the ideal gas, PV equal nRT. Huh? The first something in the topic 3. I don't know the order, first or second or something, but definitely given here. Third one, huh?
Yeah.
Calculate the pressure, meaning P. P is nRT over V. The number of mole, 6.2 times 10 negative 4. R is 8.31. T is 18. You need to convert into Kelvin. Add it with 373. And then divide the volume. 1.3 times 10 to negative 5. Okay. And you get pressure. That definitely will be the answer.
Yeah.
Truthful and Royce identified the helium gas in the B by observing its emission spectrum, along with an estimate how an emission spectrum is formed. Okay, emission spectrum is formed by the emission of energy from hot gas when the electron transfer from high energy level to low energy level. An emission spectrum is formed by the emissions of the EM wave by the transitions of the excited electrons in a hot gas, high temperature gas, huh? From high energy levels to lower energy levels. Okay. The wavelength of the EM waves associated with the difference in those energy levels. So each element or each type of element, each of atom has their specific, unique spectrum. Okay.
Yeah.
The work was first reported in a peer-reviewed scientific journal. It outlined that the Foldenroyd chose to publish their work in this way because it is one of the best way to ensure the reliability and the accuracy of the research result. You need to be a research, or when you have a an assumption and like a statement about something, you need to be reviewed by other experts to ensure that there's no error in your way of research, or how to you get that conclusion. Okay.
Yeah.
And this is one of the most important method in researching in science and technology. Okay, that's it for today.
Yeah.
6. Take it very easy. I think you can do that.
Yep. Okay.
Wow, very long. 7. Photoelectric effect. Okay, see you later. And if you want like some extra